Okay, enough of fidgeting around. I guess we are finally live. Let's then get started. Just wait a second. Yep. I guess we are finally live. Let's then get started. Just wait a second. Yep. I guess we are finally live. Let's then get started. Just wait a second while I put the phone to the charger. Yep. I guess we are fine now. So yeah, let's get going. Just a sec. Let me just connect the laptop charger as well. Just a second. Okay, so what are we actually doing today? Up until the last one, I've been just going around looking at various things. So, things we have looked at already in one way or another. Let's see. The fundamental groupoid. Similarly, the fundamental group that is there. We have seen some, let's see, in isomorphisms. And more of that. So what is on the plan today? The plan today is mainly to fill out this and make sense of this commutative diagram. Not really this one. Yeah, this one. Actually fill in this entire commutative diagram, and not really even this one. Not even this one. Where was that? I think this is it. Yeah. I guess I should just fill in all the details at this point. So, yeah. what are we going to do today? Let's see. So on the plan is to fill in the commutative square of all the functors that we are defining in order to get the groups and groupoids. And what else? Let me see. Also, I'll just be looking at all the book results. So there's that. All the results given in the book, all the propositions and proofs. Yeah, I'll just try and look at that. What was, by the way, the plan actually over there? Yeah, the fundamental group of the circle, that is also important. So we will be looking at that, the fundamental group of the circle. What else? Okay. So first, let's recall what that commutative square was. What we did, we started in top, right? From the top, we used this functor, the fundamental groupoid functor, to get a groupoid. Should I go GRPD or is it GPD? Let me just check for once what I'm using. Yeah, I guess we should do GPD, staying consistent with my own notation. Fundamental groupoid, and then from this, I guess we select one groupoid. Let's say pi1 of x, and then let's say we get the groupoid pi1 of x. I don't know exactly how to get this around, because this is not a functor. This is just you pick up one object and look into it, and that is not what you were supposed to do when in a category, but I guess this works out. And if you apply the automorphism functor on it, so then you will get, so we have to show that this automorphism is indeed a functor. Then you land in group, and in fact the group you get for each object x0 you choose is actually the fundamental group. So your x0 is sent to the fundamental group based at x0, fundamental group of the space X, of course. And on the other hand, what you can do is just select some particular object here, select one space, let's say you select the space X. From the space X, you can get this functor, which is basically, I don't know what kind of a functor is this. Okay, we'll decide on what this functor is. Where we are going is top star of X. Okay, and on that you apply the fundamental group functor. So this is a functor, and that gives you the fundamental group. So again, here you first of all choose the x comma x naught space, and then that gets sent to the fundamental group of x comma x naught, something like that. So what we are first of all going to do is we are going to fill in this diagram. And what are the things that we actually need to show? Things that we need to show is that this fundamental groupoid, this is a functor that we need to show. And I don't know what to do with this, so I guess I'll just say, make sense of it formally or something like that. And we have to show that this is a functor. We have to show this is a functor. We can just go ahead and show this is a functor as well, so that this is a functor. And I have to find what this even is. And also, yeah, there's that. Make sense of this. Okay, so there we have it. We have some work to do. It is not all trivial, but I don't think it is very difficult either. So yeah, let's go. Guys, I'll just centralize it a bit more, like that. Yeah. I guess I should just compose a playlist for me. These ones just suck. Either you have to play a long playlist by Bach, and then half the time you get copyright strike, copyright claimed, or you have to listen to this kind of cheap stuff. So anyway, moving on. First thing is that we have actually accomplished this. I have actually done this. I'm not going to repeat this on this tablet again because it was pretty tiresome, and writing all that, I'm not really in favor of writing all that. So I guess I'll just show you where I have written the stuff, and that is here. We show that the fundamental groupoid is a functor. So this is the definition stuff. We start with the homotopy of paths. First define what a path is, and path homotopy we get it is homotopy relative to the endpoints. The endpoints are always fixed. Then we define the star operation by the concatenation, And then we move towards the groups more. We define the fundamental groupoid. See, the fundamental groupoid is a functor such that for a topological space X, the pi1 of X is a groupoid whose objects are the points in the space, and morphisms are path homotopy classes of the paths. So it's all the stuff that we have defined before. And this P of X, X naught quotiented by the homotopy. Yeah, this I even defined this as well during the stream. But then we actually need to show that the fundamental groupoid is a functor and it does all the things that it is supposed to do. So for that, what do we need to show? To show that the fundamental groupoid is a functor, we need to show that for all topological spaces, first of all, it actually, the codomain is actually GPD. So it actually gives groupoids. So for any topological space X, pi1 of X, okay, what was that? Okay, so for any topological space X, pi1 of X is a groupoid. We need to show that. Then we need to show for any continuous map gets translated to a groupoid functor, because remember it has to be a morphism in GPD. A morphism in GPD is a morphism between groupoids. Like, since groupoids are categories, morphisms between groupoids is a groupoid functor. So there's that. We have to show that pi1f is a groupoid functor. There's one curious thing that, yeah, we defined pi1f much later. Did I even define it? Yeah, I defined it like that. Pi1f, it takes a path P well, wait up a bit. Okay, first of all, yeah, true. Okay, I see. Groupoid functor. Okay, then it has to send each point to each point. Okay, we have not really shown that. So in here we have to show that something, this is a functor. We have to show that something else is also a functor, and we have not even defined it completely. So okay, we have to complete this definition and all that. The identity map gives the identity functor on groupoids. Composition of maps gives composition of groupoid functors. So it is all the usual functor stuff that one has to prove. So this is the definition of a functor. Where did this disappear from? Anyway, whatever. So this is the definition of a functor. A functor f from C to D between categories C and D consists of a function so it sends objects to objects, and it is supposed to send morphisms to morphisms. Compositions are preserved and identities are preserved. Notice how uncannily similar it looks to homomorphisms. So yeah, homomorphisms are just functors. They're just functors. Before functoriality, people lived in caves. Okay, there's that. Okay, so the proof is not really complete here. We have to complete the proof actually. Let me just check in for a second. What even is going on? Okay. So first things first, we show that pi1 is a groupoid. So to show that pi1 is a groupoid, how did we define pi1 of X? Whose objects are points in the space and morphisms are path homotopy classes of paths between objects. So for that, It's a groupoid because objects, we know what the objects are. Objects are the points in space. We have to just show that the morphisms uh, behave properly. All the morphisms are isomorphism. That is what exactly we need to show. So there is a reverse for any path f from x0 to x1. There's the reverse path, which you just traverse backwards on it, and by the this is the path homotopy that gives you the exact thing. So this is the one we were actually talking about all that time. Let me just show. It should be somewhere up here, not really here, more up. Yeah. So this is the thing that we were talking about, that we go less and less outwards, and some kind of a cone, not really, etc. So that is the kind of stuff. Then therefore we show that f star f bar is homotopic to the identity map, or the constant map rather. So we get that every morphism is an isomorphism, and pi1 of x is indeed a groupoid. For any path p, okay, then what do we need to show? We need to show that the continuous maps gives a groupoid functor. Okay, we check in on that later. The identity map gives the identity functor. Where is the identity map, by the way? Consider identity map from x to x. We see that idf of x, by the definition of the groupoid functor, does it really? Okay, so I just defined the functor on the morphisms, and I did not define the rest of it, so I have to define the rest of it. Okay, so I guess we are just now going to define the rest of that functor. Yeah, sure. We have already defined that for any continuous map f from x to y, pi1 of f is a functor from pi1 of x to pi1 of y, such that this you have to change that is a functor from pi1 of x to pi1 of y, not this, such that the following hold. Let's do with that. So what are the things that we want to hold, that we want it to hold in, or whatever? We want that it is true that first up, we want that pi1f of some point x is just f of x, right? So this is not pi1 of f of x, this is pi1f of x, something like let's say something like this, pi1f of x. Maybe I could just put this in a bracket or something. Yeah, so I want that this is true, for all objects x in pi1 of x, or rather I should see calyx here. By the way, what is this piece? 24. Okay, once again Einaudi. He picks up some nice tunes, but composes like shit. Anyway, pi1f of x, f of x for all objects So there we see is that enough? Is that enough that we do this? And pi1f of, let's see, a map from x0 to x1 is, let's see, it is the class of those maps, just the paths, the path composition, like that. For from x0 to x1 in pi1 of, yeah, I guess that makes sense. I think this should suffice. I think this should suffice. Okay. There should be a bit more space here. Okay, so I need to check that this kind of a pi1f functor that I defined was even valid. It is actually legit. We have to show that this is a legit functor. So for that, we cannot start for any path. We have to start. So to show that pi1 of f is a functor, what we need to do is follows. Let me just see. So show that this pi1f is a functor from pi1 of x to pi1 of y we show the following. So what are the conditions that we need to show in order for it to be a functor. That is, first up, we have indeed a function from the object to the objects that we have already defined here. We have defined this function which takes some point x and gives us back the point f of x. So I guess that is good. And a function f from, so it needs to send maps to maps. We have defined how it sends maps to maps, but it has to satisfy a few conditions. Compositions are preserved like that, and identities are preserved like that. So we just need to show that these two, are satisfied. So there's that. Composition preservation. What is that like? Say we take it like that. This. Okay, first of all, we actually need to show that this thing is well defined, that kind of function thing, because we used representatives. So we were using equivalence classes here, and in the definition of this kind of a functor map, and whenever you use some representatives from equivalence classes, you need to show that it is indeed well defined. So we have actually shown that this is well defined for any path from x1 to x2 is a path from this f composed p is a path from f of x0 to f of x1. That is true. Continuous images of homotopy paths are homotopy as well. So this is well defined since this, okay. Okay, did we show that this is a groupoid functor? Defined it for objects. So it sends the identity object to the identity there. Yeah, this looks like. So the functor at the identity, functor takes the identity at the object and gives back the identity of the image object. So that is like this. So it takes the functor takes the identity of the object and gives the identity of the image object. So that looks fine. Okay, so we don't need to write that again. We have already shown this. Pi1 of f with p. So that is we apply pi1f on p and q. Let me just zoom this a bit so that's a bit easier to see for you. Pi1 we apply pi1f on pq. I guess, oh my goodness, yeah, I guess I can fix the bracketing here. I think I would like to have these guys outside and this guy inside the bracket. So I guess that helps it. Yeah, it does. So pi1f applied on this composition pq is actually just pi1f applied on the q star p. That is how composition was defined, right? So then again, by the definition, you send f inside and compose with these. And this is one property of the the path concatenation, that composition distributes over it from the left. So yes, indeed, this is. So the one thing I did not write in between, that this is equal to f compose q, that thing, start with the path f compose p, and that breaks out like this. So I should have just written this in full. I have not written that thing in full properly. So that thing should be equal to pi1 f of p composed with pi1 f of q. So I guess that works. Yeah, I guess that works. So where should I really put the I would include another step and fix the alignment a bit. That another step would be this. It would be f circ f compose q star with f compose p. So yeah, that is the step I would include in between. I guess I can just put this after that. That should fix the alignment. Oh no, it does not. Okay, that botched it up horribly. I guess this is the middle, right? And also I did not bracket this part. Oh, I put the wrong bracket. Okay. Touche. Now this should be fine, and we align here. Or should I align on the right? Aligning on the right just looks weird. Yeah. Also, I'm aligning this on the left, so yeah, that looks fine now. But it doesn't really. Okay, that guy needs to slide. That guy needs to slide. Is there any step that I can skip here? Don't really want to skip any steps here. Yeah, I guess I will leave it like that. Small imperfections here and there. That's what makes a human a human. Anyway, so we have actually shown that pi1f is a functor. I guess we need not worry about that anymore then. So what is next? We need to show that the identity map gives the identity functor on the groupoid. So identity map takes the identity. So we apply the functor. I showed that it is the identity on the, it is the identity functor on the groupoid. That identity, the identity functoriality I showed only for the maps, only for the morphisms in the groupoid, and not really for the objects of the groupoid. So I guess I need to show that for the objects of the groupoid. Going into this source code is like jumping into cold water filled with crocodiles. We see that first off, we see that pi1 id sub x of x is equal to just id sub x of x, and that is equal to x, and that it works for the maps. So it is not much work, but small changes here and there. So pi1 preserves identities, maps from maps to groupoid functors. I guess that last bit was not really necessary. I'll remove that. So pi1 preserves identities. There's that. Finally, what do we need to show? Composition of maps gives composition of groupoid functors. Composition of maps gives composition of groupoid functors. Let's go. Finally, for f from x to y and g from y to z at a path p and x, we see that this is this, right? Because that is the definition. But now we can use the associativity of the composition. So if you want to be really petty about it, you can just go ahead and plug in the associativity of the composition stuff. There's that. With that, I need to include equal to G circ F on P, right? I guess that's a bit more accurate than before. So yeah, here's the associativity of composition of maps. Pi1G F compose P. Yeah, right. So I guess I'll just put a bracket around that as well, because that makes it more clear. Where is that? Pi1G, yeah, Pi1G F compose P. Now this F compose P, the class of F compose P, that was exactly applying the functor on P. But what is missing here is that we did not show that it takes on the objects. So I guess I'll just add that line, because this proof, having to write this proof is really petty. So if I'm doing something petty, then I'll just do it properly. At least we see that okay, that's going to be a hassle. G circle F of X equal to, yeah, I mean, okay. So what is there to actually show about objects? What is there to show about objects? We need to show, okay, yeah, I know what is there to show about objects, of course. Oh my goodness, that is really petty. That is extremely petty, what I'm going to do now. That is extremely petty. We have to show that this, just watch this out. We have to show this abomination. So this, by the definition, we know is G compose F on X. We know that by the definition. This we know by how composition works, blah blah blah. This is equal to, since this is, we are applying G on something, this is G of F of X. This is actually the functor pi1G applied on F of X. Just imagine how much we are, like, how much fluff we are having to write. And since applying this F of X is just applying the functor, we apply the functor again. So pi1G, now pi1 F of X. Oh my goodness, that was probably the pettiest thing I've ever done in my life. Oh my goodness. Okay, that and is really sticking out in the middle, so I guess I'll just remove this entire thing. I have to put this entire thing in a line now, otherwise that will look horrible. I also see the following. Whenever you have to prove that something is a functor, you have to do that. We see the following kind of a thing. Oh my goodness. Just get up. Don't. Oh my god. Just get up. Yeah. Nice. Yeah. Okay. This is so very petty. Where should I align these? Now I'm in dilemma. These are already aligned, or are they? This looks similar. This does not look similar. So I should align them here, or align them here. If I align them here, that would look pretty terrible. I'm sure that would look terrible. If I align them here and here, that would look pretty good. Yeah, that. Oh, okay. I learned even at the wrong place there. Not here. It was not supposed to be here. It's supposed to be here. Oh, it looks fine. I guess we'll go with it. We can go with that. We do not need that this line in the end. So this is absolutely some petty stuff that I'm doing right now. Yeah, so know that this is very petty. Okay, so I think that is the complete proof. I mean, this is just looking horrible. I'll change that. I'll not have this guy. I will remove this guy. Yeah, sure. I'll remove that guy. That just looks so horrible. Yeah. I guess it's fine now. Yeah, it is a bit right aligned. I guess I can find the middle. This is the alignment, right? This is the alignment. I want this to be around this composition or the bracket or even Q maybe. I'll just put that in between the bracket and the Q, because that's where it makes the most sense. Just put that here. Yeah, it looks weird, but yeah, you gotta do what you gotta do. That now looks totally fine. I'll pretend that it does. Yeah, I guess actually seeing that screen. Yeah, yes. So okay, there's that. So what did we show? We showed that pi1 is a functor. Pi1 is actually a functor. It does what it promises to do. Okay, that took a while. What else are we going to show? So I guess we are done with this part. Pi1 is indeed a functor. Now we have to show that the next thing I'm going to do is show that this automorphism is a functor. I'm not sure where to write that, so I'll not put that in the obsidian right now. I just go on like this. So show that automorphism so this is what it does, right? Auto functor. You have got a groupoid pi1 of x. What odd does is it picks this object x, in the pi1. So it picks just a point, and it gives exactly what you think it gives. It just gives the automorphism of x. If you want, you can just be even more petty. You're just being very petty today. Yeah, just gives this. Yeah. Also, know as a fact that that applying this. Okay. Oh, great. Finally some Chopin. Yeah, I can just play the Chopin nocturnes actually. Pretty sure there are some copyright free ones I have in my collection. I remember them being there. I'll just go ahead and play some Chopin nocturnes. So, enough of that nonsense. I'm not really sure if I play a Rubinstein's recording, I might get copy striked. I'll just try once. Rubinstein's are the best. Somehow you can download this. This download option is still here. Oh, okay. Not really. So this music comes from this album. And who owns this album? Okay, Sony owns it. I can't play it. They'll just suck all of the blood out of my body. Sony. This is owned by Sony. I can't do that now. Okay. Okay, let's do this one. I used to like this album. Yeah, that works fine. This is good. Let's go. So got good music. Let's do some good maths. So what do we need to do here? We first need to do something with the how the ought functor actually sends the morphisms. So what we are going to do here is remove this. Just remove this. I don't want to see this. This is just out of x. I want to remove that abomination. So one way one can define ought of x is like this. Ought of not x, ought of this morphism p, where should I do this p actually? Yeah, sure, why not? This class of p would be where p is, where this class of p is the morphism from x0 to x1 is, I'll do it like this. This should go to, okay, where even should this go? This should go to a morphism from out of x to out of x0 to out of y0, right? Out of x1. So that should go there, right? Now pick some f from, yeah, let's do this. Let's pick this f. Oh, I see. Okay. Is a this is a morphism, or let's see, this is an isomorphism in group from out of x0 to out of x1. What should that be like? Suppose we have ought p here, and we apply this, where f is a path from x0 to x1, or rather I should denote it like this. This should really be so let's see, there you got x0, they got x1. Here is the path or the path class between them. There's this automorphism. So how should it give a loop at x1? We should go reverse this first. So go around that, take this loop, so go around that, take this loop and come back here. So that should be, you come back after taking the loop, after you go around there. Or this is also, let's see, this should be something like, oh no, I cannot do that. I guess. Oh, can I? Yeah, this should be the class of P inverse star F star P. But I guess I should not write that. I should not really write that. So we know that yeah. So if you just remove the classes right now, if you denote it like this, that x0 to x1, so ought P of F should be PFP inverse. How is that? And this is indeed in the automorphism of x1. Right? That is so good. Yeah, so last time, for the last time formally, we need to define for P from x0 to x1, define the morphism out of P from out of x0 to out of x1. You know, the notation is pretty parallel, so it all matches as follows. You define it by this, by some f for f in out of x naught. So f from x0 to x0, we define ought P of f to be PFP inverse, and that is in ought of x1. That is because you see that you go from x1 to x0 to x0 to x1, so you get P inverse F P. So this one is indeed PF P inverse. I guess this is all fine. So that is how we define it on morphisms. Now we have to show that it respects composition. Okay, so we show that. What respects composition? What is that like? what does it mean to say that ought respects composition? Let's see the definition and just have a look at the definition. So f in, so given some p from, let's see, x0 to x1 and q from x1 to x2, we want ought of qp to be equal to ought p compose ought q. Okay, so that is pretty easy because this is, you know, conjugation type of stuff. So let's see, ought of qp on f, where let's see, f is from x0 to x0, so f is really an automorphism of x0. So that is qp f p inverse q inverse, or rather qp inverse, that is equal to qp f p inverse q inverse. I'm having real deja vu right now, like I'm having super serious deja vu right now. So this is ought p of f, this is q inverse, so this is ought q of ought p of f. That is fine. That is fine. And we need to show that ought preserves identities. Ought preserves identities. That is to say that consider the ID x in ought of x. ID x is in ought of x, right? Oh no. Consider ID x. Yeah. We know that, we see that ought of idx of, let's see, some f, where f is in ought of x, that is equal to, this is very boring, idx f idx inverse, these are all identities, so this is indeed f. So yeah, so that is identity of ought of x on f. So ought of x is a group, right? Ought of x oh yeah, we did not show the most important thing, that ought of x is indeed a group. We need to show that. So f, okay, this is really just way too much. Ought of x has an identity. There is an identity on x. This guy belongs to ought of x. Okay, just hold up a second. Hold up a second. Now I'm just getting more and more lost in the notation, in the absolute forest of notation. ID of x does belong to out of x, right? Because ID of x is a morphism from x to x, therefore, and since all morphisms are automorphisms, ID of x is an out of x. What else now? See that? Okay, now I see. Out of x is a group. For that, what do we need to show? We need to show the following. That for all, how is group defined even in this categorical situation? We need to show that there exists an identity. Let's call this bold one for now. In out of x, such that what? Group in what sense? Just composition group? It is. Okay, it is a composition group. Okay. Yeah, it is a composition group. The set of automorphisms of anything is a group that is well known. So, out of x. Yeah, this is fine. If for any category, odd C of x is always a group. But odd sub C is not always a morphism, not always a functor. Functor from C to GRP. That is because functor is more than just sending objects here and there. Functor sends maps as well. And unless the morphisms have really something to do with the automorphisms, you cannot in general translate them through automorphisms. We will talk about this later on as well, but this is like need-even category theory. I don't really want to get into that kind of thing. I want to do some algebraic topology right now. So yeah, we did show this thing, that automorphism gives a functor. We are done here. Just wait a second. Okay, yes, so we are 1/3 done from what we started with. Make sense of this one space. We will make sense of things later. Find out what this even is. Turns out I cannot spell is. Okay, so we now show that pi1 is a functor. That is what is remaining for now. So we need to show that pi1 is a functor. Instead of this subcategory, what we can do is here we can take a something happened, some weird thing happened. Yeah, we can take a different path. That is, let's see, let's do this. Let me just move all things around a bit. I love this nocturne. This one's so beautiful. Okay. So what about we embed this, this being a subcategory in this. So inclusion functor, this is some kind of an inclusion functor right here. So that is a very meta thing about categories. So I don't really want to get into that right now. Let's put this on top here. We functor this inclusion or include this functor or functor this or function this include to top star. And after all, from top star to GRP, we know that this top standard functor pi1 fundamental group, this is a functor, and that is what we show now. So pi1 is a functor from top of X to GRP. That's probably one of the more important things that go on. So given x comma x naught, how do you even define this object pi1 of x comma x? How do you define it irrespective of this groupoid thing? So how you define it is as follows. You define this object. How do you define this object? To be, let's see, you define this object to be this. You quotient omega of x comma x by path homotopy. So what that is, now how do you define omega of x comma x? That is defined to be the paths from 0, 1 to x such that f of this are both equal to small x. So that you quotient this, so this path homotopy So this, by our previous notation, this is just p of x comma x, right? By how we took our previous notation. So this path homotopy, path homotopy is an equivalence on omega of x comma x as well. So we can quotient it, define it like that, and the operation is defined as follows. So suppose you have a class of paths f and you operate that with class of paths g. We define it in the stock standard way to be g concatenate with x. So first you go g, then you go f, and that is, I guess, the usual stuff. For this to be a group, we need to have that. Okay, so we know that f on f bar is equal to f bar star f, which is, since f bar star f is homotopic to the identity, this is the homotopic to the constant map on x, which is the identity. Or since this is a group, let's call this E. And similarly, we can show that E is also f bar as f. So we see that f inverse, this class of f, is really invertible, and the inverse is the class of the reverse map. So there you go. We see that there is an identity. Okay, yeah, identity is defined to be the class of the constant map. And note that concatenating the constant map does not really change anything. This constant map will really be just, the constant for some time, for half the time constant, then suddenly f, and that would be just f. And similarly, you go constant, you first quickly finish f, then you go constant, and that is also the same as going f. So yeah, I guess that makes sense. Yeah, I guess I'm in mood to define the explicit homotopy. Let's define the explicit homotopy. Yeah, I'm in mood to do that. Explicit homotopies. Those are as follows. We show that the constant map concatenated with f is homotopic to f, and f concatenated with the constant map is homotopic to f. We define the homotopy as follows. L of s, or rather t comma s, is defined to be this concatenation looks like that, right? So x for t being less than equal to 1 minus s over 2, and f for t being greater than equal to 1 minus s over 2. Yeah, and right concatenation that at t comma s, I will define it like this. F of t for t less than equal to 1 plus s by 2, and x for t greater than equal to 1 plus s by 2. So I guess those define explicit homotopies for exactly what is going on. So there is that indeed. So yeah, first thing we have showed that pi1 of x comma s is a group. We have shown that this is a group. Now I need to show that pi1 is a morphism. pi1 is a morphism. Okay, what does pi1 do to maps? Let f be a map from x comma x to y comma y. What should pi1 of f be? So we know that pi1 of f is supposed to be a map from pi1 of x and to pi1 of y. How do you define? In fact, note that for this map, this pi1 of x is usually denoted like this. Pi1 of f is usually denoted as f star for some reason. This has been going on around in pretty much all of the books that I have seen. So there's that. How does one do it? So what are the objects of pi1 of x? You take an equivalence class of loops based at x and you do something with that. Now I'm going to define it like that pi1 f of some class of loops, I would define it to be the class f circle p, because here you have x and you've got loops and you apply the map f to it, continuous map. That should also result in some kind of loops around y, right? Those should also result in something like that. So first of all, we check that this is well defined. If P is homotopic to Q, it is actually path homotopy, but yeah, this is too much to write. Say there is this P from S T. There's this P from I, or rather from cylinder S1 cross I to, I should just change my notation here. I should change my notation. S1, yeah, that is a much more happier notation. So check this out. have no idea how to write the math bold S. I'll just look at what it looks like from here. That looks super weird. That just looks weird. So there's this big cusp and there's a small cusp. Yeah, whatever, I'll just write it like that. Yeah, that's fun for me. Let's see. The dollar is okay. The dollar is okay for me. So S1 cross I, you have that homotopy P to X, and from here you have the map F to Y. Therefore, you have this homotopy P compose F. Moreover, in this homotopy, we know that, blah. That's just blah blah blah. Yeah, it works. Like, you even see that it works. Okay, so this is well defined. What is next? We need to show that since this is supposed to be a group homomorphism, since this is supposed to be a group homomorphism, so what it needs to be is that pi1f on P composed with Q, let's see, class of Q composed class of P oh wait, F, am I missing something? pi1 of x, okay, I see. pi1f applied on this class stuff. We know that this class thing is P star Q, and that again becomes f of f composed with P star Q, and that is f composed with P star f composed with Q, and that is pi1f of Q on pi1f of P. So we need to see this is a group homomorphism. Oh, to be a group homomorphism, yeah, that is enough to check for group homomorphism. I sometimes forget what exactly are the things that I need to check and what I don't need to check. Okay, so what needs to be done next is I need to show that this functor respects composition of maps. So G of F on P, that is the class of G on F on P, so that is the class of G on P on F, so that is pi 1 G on the class of F on P, that is pi 1 G on pi 1 G on the class of P. So pi 1 of G compose F is really pi 1 G on pi 1 F. So there is that, and there is the identities. What is the for the identity map, pi 1 of identity on any loop, let's say like P, gives identity compose P, and that is just P, and this is the the identity on group, basically the identity in this group, of course, pi 1 of x comma x of this F. What? Just wait a second. Yeah. This isn't pi 1G, right? I'm confusing it with, I think, the fundamental groupoid, where these were morphisms. Is a group homomorphism. We show that it is a group homomorphism. We saw that it respects composition of morphisms, the identity, okay, so this is actually identity on x comma x. Yeah, this is applying the identity on the pi 1 of x comma x on P of, so this is like that. So indeed, we finally see that pi 1 is a functor. Now, these are the steps that I cannot really figure out entirely on myself right now. Let's see what I can get from the other place. Okay, so the thing is, what we have at hand right now, it would take at least 2 more hours to completely pin down and get it properly going. So it will take at least 2 more hours to do that. So this is going to be a long one. Yeah, this is going to be a long one today. I'll be back once again. Then we will together analyze exactly what are the things that we are being pointed to. Well, I guess I'm back and ready to encounter whatever mathematical horrors and wonders are coming up. So, turns out that when we were looking at this diagram, these things of selecting something, these selections are true selections, and you cannot really have a good way of selecting it. That is to say, there is no functorial way of selecting things. So these selections that we make to pass from topological spaces to pointed topological spaces based on a single space X, all of these things are basically non-functorial choices And the fundamental reason being that there is no natural functor. There is no natural functor from the topological spaces to the groups, which basically gives the fundamental groups of spaces. So that is the thing, that there is no natural way of doing this. What you can do instead is, given a space X, what you instead can do, we can get a family of groups instead. So this is something which we can do. Okay, so that will be our current goal, that given a topological space, so we are basically going to construct a functorial. This, we are going to get a family of groups. Now what this exactly is, those are the things that will be basically getting out. Let's have this once again. We are going to get knee deep into category if we try to do all of this, but yeah, we can start. Probably we can spend some more hours on this, probably this entire stream on this one thing, and we'll not be doing any books. So yeah, no book stuff, only this. Let's go. So what we can do is something like this. Let's say you start from the topological spaces. Let's say you start from top. From here there is of course there is the fundamental groupoid functor. So you can go to the category of groupoids by the fundamental groupoid functor. There is that. And also what you can do is you can go to a certain kind of fibration of topological spaces, which is this family of topological spaces. I'm not sure exactly what to call this functor though. Let's see, what name does this guy like? Let's call this sec for some reason. Okay, I'll go with it, I guess. So from here, what you can do is from here you can just directly go to groups, but not exactly groups. You can go to family of groups. This is done by the OT here, and this is also done by not exactly this though. Is this fam top or is this fam top star? I'm not really sure right now. Okay, this is fam top star. Yeah, this is fam top star actually. Okay. And given now, after you have attained the family of groups, all the fundamental group family or the fundamental functor family, whatever this is, once you have attained the family of groups, basically all the fundamental groups that are possible on a certain space, so this functor right here was our goal functor, right? This is what we wanted all along. Given a topological space, to find all of its fundamental groups at once. So yeah, on this what you can do is now you can apply just one free choice. You can just apply now one choice to get something in group. So yeah, there is no natural thing from, so you can basically now do this thing but here. So that is what the goal is. So this is what we reduced our initial problem to. This is what we are doing now. There you go. This is the entire thing that we are doing. Let's centralize this, and this is the main theme of our actions. Maybe I'll just make this a little bit bigger so it gets the emphasis it deserves. This is the thing we are up to now. So for that, we have to understand a few things here and there. Namely, what on earth is fam? And also we can figure out a better way of looking at top star by considering this fam thing. Also, what is this fam of pi 1? So we are doing fam of spaces, we are doing fam of functors. Is this some kind of a functor on big spaces or something like that? Let's just look out for that. Also, what are these functors exactly? Like, what are these? Also, what is this new art now? It does not grow to groups now. It does not start at one groupoid. It starts with the category of groupoid, and it just somehow lands in a family of groups. How does that work, and what is it exactly? Let us figure out all of these things one by one. So to go one by one, our first major point is what is fam? What is this thing exactly? That is what we are currently interested in knowing. Just wait a second. Let me just get a grasp of exactly how poor it looks on the screen. Yeah, it doesn't look that bad. It looks bad, but it doesn't look that bad. We can do with this. Yeah. So I'll probably change this. This is our first question. What is fam? So, what is fam? To be very precise, to be absolutely, completely precise about this, fam is a two functor. Fam is cat to cat. Fam is a two functor. Fam is a two functor. How many times do I need to repeat that to understand it? Well, let's stop crashing out. Really? What is a two functor first of all? Meaning, it takes a category C to a category fam C. So, given the C, you go to a category called fam C. Quite fancy, have to agree. It takes a functor. So suppose we have a functor f from C to D, right? That gets taken to a family functor, fam of f, from fam of C to fam of D. Okay, and it acts on natural transformations as well. So there is that. So suppose we have a natural transformation alpha from, let's say, this functor f to this functor g, where both of these functors are from C to D. That gets sent to another natural transformation. Yeah, not much actually. That gets sent to this natural transformation, fam alpha, which is a transformation from fam f to fam g, where both of these functors, fam f, fam g, are from fam c to fam_d. That's quite a lot of maps, right? Okay, fam is a 2 functor, but exactly what are the details that are working behind it? So let's see. Uh, what is, first of all, okay, just let's start from this layer. Let's start from this layer. Given a category C, this is the first part question we are asking. Given the category C, what is fam C? Let's see. Okay, so what the clanker says is that fam C is the category of families of objects of C, equivalently a free completion of C and the small coproducts. It is sometimes called the free coproduct completion of C, the category of C indexed families, or if one is more abstract, the growth and deconstruction of the constant pseudo functor. That means a lot of things to me, I guess. Objects of fam C. So an object is a pair. So let's start from objects. Object of fam C is an indexed family of objects of C. Well, as if that makes a lot of sense. So first up, how to get an object of fam C? First, choose an indexing set. Choose an indexing set. I, let's call it. Okay, you got an indexing set. Now choose this family. What is this family? This is a family AI, where AI are objects of C such that I is in I. So it is basically this family of objects of C indexed by I. And this thing is exactly an object. So this thing, this thing right here, this family of maps, this is in the objects of fam C. Quite fancy. You can think of an object as a disjoint family of objects in C indexed by some set. Okay. I guess that is it. So objects of FAMC are just um, families of objects. So in a kind of set theoretic way, object of FAMC is kind of like let me just make a symbol here which will not be mistaken by anyone for anything mathematical, so this is completely non-rigorous. It's kind of like the power set on the object of C. You get all kinds of families, but not really. This is a product, co-product, I don't know, but this is an object. We have decided what the objects of FAMC are. Now, what are the morphisms of FAMC? So you have this object set of AI indexed by I, and from that you have, we are talking about morphisms of FAMC. So given these objects, let's see, AI indexed by I and BJ indexed by J, one has to have this morphism, and so for the lack of a better name, let's call this, I don't know what to call this, let's call this F. So such a morphism S has first of all a function which is like this from the two index from one index set to another, and a family of morphisms. Okay, and a family of morphisms indexed by I. So what is this family? This family is something like phi sub I from AI to B f of I, where I is this. So you got this family, and this all is contained within this one morphism F. So it has a function and a family of morphisms where this phi I, let's see, let me just make this a bit more verbose perhaps and a bit more precise. Phi I is in the hom C, is in the category C, a morphism from AI to Bj, such that J is equal to f of I, and this is all indexed by I. This is exactly the family, which is this. This is a certain family indexed by I. composition is defined in a natural way. Okay, yeah. So given morphisms, you have some other stuff to check as well, because this is a category and we are not kids anymore. So given morphisms, you have to check the following things, which is this is like unnecessary. This is complete nonsense. This one, you have to have a composition of morphisms, you have to have identity with respect to the composition, and you have to have associativity. Associativity will be clear enough from the definition of the composition. So I think we should focus on how to define the composition exactly. So yeah, let's define the composition. Morphisms. What is this? Suppose you have this morphism. Wait. Suppose you have f. Okay, not like this. Let's write it like this. xi indexed by I to, suppose there is this morphism f, to yj indexed by j. Then you have this morphism g. You have z k indexed by k. And so here we have the most natural way to define composition, the composed index map. G compose f from I to k, and this family of morphisms. And suppose f has the family, let's see, f has the family phi I, and g has the family psi j. Then we are composing, then the family is, then we have the family, let's be a bit careful here, psi of f of I composed with phi I. Yeah, I think that is it. So this would be a morphism from xi to z, well, gf of k, gf of I, in fact, indexed by I. So you get the family like this. So this is like, you have this family, you have this family, you have this family, and from all the xi you get some maps like this, you got morphisms like this. And so this is the data of this morphism, and in this morphism, suppose you get something like this, there's some stuff going on here. So indeed, in the composed morphism, you get things like, oh goodness, okay. In the composed morphism, you get things like this, this, and this. This is the kind of thing you'll be getting in the composed morphism. So yeah, these things are of course not very intuitive, but such is life. Okay, there we have composition of morphisms. One important thing that I would like to do is identity morphism. What would be the identity morphism actually? That is a good question. What would be the identity morphism? Well, the identity morphism has to be something which can compose with anything. So let's see first. You have this family, then this family, then the identity on this. So given the identity on this, yeah, I guess you just sent all the xi to the xi, something like this. You just translate this copy like that. So this is like that, something like that. So I think for let's denote this by something. Let's see, maybe calligraphic x, for x being this family xi and x by I. We define identity this morphism identity on this cal x has first of all the identity on the index set I from I to I, and this family identity of each xi says that I is an I. So the identity morphism for anything would be this. This also works out not only for pre-composition but also post-composition, and that is because how much space we got. Even we got some space. Let me just do some more acrobatics with this. This needs to go here. I'll actually make this smaller, show that I forgot about this. I'll even make this smaller as well, because it is not that important of a picture. Or maybe show this here. Okay, so the identities, you have got the pre-composition identity, and now you have to get the post-composition identity. That's like this. So you get this family like this. You got the same family. Oh man, what the hell? Wow. This somehow got smaller. Yeah, I guess this is good. So what you do is you get something like this. Once you decide that you want to go crazy, you don't go a little crazy, you go completely crazy. Let's say this is the identity, and from here you can have any map like that. Okay, so there you have identity, pre-composed and post-composed. We are still in the first question, and I think we just ended the first question. Like given a category C, what is fam C? I think we answered that question. What is fam C? Now comes the next question. Given a functor, then comes the next question. Let's cover this completely. If we are covering this, then let's cover this completely. Given a functor f from C to D, what is this family functor from fam C to fam D? Let's see. Okay, so it turns out that given a functor from C to D, this is a functor. Let's define the family functor. Let's see. By, you have to choose some object in fam of C. Choose an object in fam of C. Let's see, something like AI, index by I. You send that to just f of AI, index by I. You keep the same index for it. So this is how fam is being defined on the objects. Now, and we need to define it on functors. This is how the fam functor is defined on objects. Now on morphisms, suppose you have a morphism. Why did the etude start playing? I did not sign up for that. Okay. Let's see. Let's have Nocturnes by Moravec. By the way, who owns these? Nonis. Okay, I guess we can get away with that. This is Moravec. quite tasteful. Let's see, let's wait up a bit. So given a morphism f from, let's say, this family ai indexed by I to bj indexed by j, let's see, this morphism fam ff this should be a morphism from, let's see, this family f of ai indexed by I to f of bj indexed by j let's see, this is supposed to be a morphism. This is supposed to be a morphism. There is nothing to worry about. This is supposed to be a morphism. This is supposed to be a morphism. That is like, wait a second. So what it does is, first of all, this fam ff just sends some I to f of I. So it does not do anything to the index things. So indexes are treated well. Indexes are good to go. And suppose we have this family, and this family phi I is sent to this family. Apply the functor on phi I, functor phi I. This goes from functor ai to functor b f of I, this family indexed by I. So this is really how it works. So first of all, fem f of f has to be a functor from this to this, so it has to send composition to composition. Let's see. Oh man, I can't do this composition anymore. This is ginormously tiring. Suppose we have this morphism. This is going to be a hell of a tiring thing, but I guess that would be worth it. No, not like, let's not draw this like this. Let's draw it like this. AI indexed by I, morphism to bj, or rather let's say xi, yj indexed by j, then morphism g to zk indexed by k. We have this composition. Let's not draw it here. This is gf. Suppose we have the family of maps here. Let's see, phi I. Suppose you got here phi I, indexed by I, and suppose you got here psi j indexed by j. Suppose this is the morphism data you have. Where does this get carried to? This gets carried to here, to this morphism. You have f of ai and you have this morphism. Let's see. Oh, no way. No way. Let me just check my sanity for once. Category. Fam of C. My goodness. Okay, let me just reload my brain. This object, this is in let's say fam x, this is in fam y, this is in fam z, right? Or is it? Oh no, this is all in fam c. Oh my goodness. Wait. No way. Yeah, these are all in fam c. And these are now all in fam d. Okay, yeah. Okay, this is in fam d. not ai, xi, this is yj, indexed by j, this is zk, indexed by k. What is this morphism now? This morphism is fam f of f. This is fam f. This is fam f of g. And with this morphism, you of course get fam f of gf. Now, does this diagram commute? The question is, does this diagram commute? And we have to find out that it really does, but how? Oh my goodness, I can't anymore take this. What is the data of this fam f? The index is still f. This would be f of phi I. This would be f of psi j. Okay. And now this gf has the data like this: psi f of I phi I. I'm pretty sure there should be a better representation for all this. Let me just restore that, and actually let's pass to triangle. Triangle is a better choice for these things. Let me just make all these smaller so that I can actually fit the more important stuff here. You can still see them, because you know these three object commutative diagrams, they're really made for triangles, commutative triangles. Just move on to more geometrical stuff. So anyway, here's the triangle. Here you go. You have your xi indexed by I. The morphism is this. Then you have zk indexed by k, and now you have this. We know that we have here this morphism f, which has this data, which has this family of maps phi I. Similarly, we have here G, which has this family of maps psi j. And finally, we have here GF, which has this family of maps psi f of I composed with, okay, let's get some bigger place, psi f of I phi I indexed by I. this is indexed by I, this is indexed by j. So here we have this triangle which commutes. Now we make another, we apply the functor, we apply whatever functoriality we have, we apply fam on it or whatever. Oh yeah, we are already in fam f. What was this, by the way? Is fam of f a functor? Okay, yeah. So here we are inside the category. So here we are inside the category fam of c. See, here we are inside the category fam of c. We apply the functor fam of f now, and we land with something fam d. Is it like this? Let's see. On one hand we have xi, not xi actually, f of xi. I just won't bother writing any braces, parentheses anymore. It's just a waste. Here you have the object functor yj. Here you have the object functor zk. Let's move this down slightly bit, like this. Yeah. Suppose we have this. Now this gets sent to, oh my goodness, fam f of f. This gets sent to fam f. I don't even have place for writing. Fam f of g, and this gets sent to fam f of gf. Now let's see if this diagram commutes. This guy here has the following data. The data of this guy consists of maps f phi I indexed by I. Here we have the data f let's see, f psi j indexed by j. Here you have the data. Let's see, f of psi f of I. I'll just write fi. I don't care anymore. Phi I, of course indexed by I. Now the master stroke comes in. Because we know f is a functor, this we know is f of psi fi, f of phi I, indexed by I. Let me just write these things, rewrite these things properly a bit. Phi fi Oh my goodness, let me just put back the parentheses. I'm pretty sure this level of detail is not actually visible on the screen because, oh no, it is all actually visible. That's great. This is f of I. Okay, mate. Therefore, this data is actually carried by the composition of fam f and fam g. You notice? This is the data carried by them. So therefore, indeed, this this morphism is indeed equal to fam f f fam f g, or rather fam f g fam f f. There you have it. The triangle commutes. My goodness. This was just a composition preserving part of the functoriality, but my goodness. Okay, now we also have to show that this construction right here preserves those things. What are those called? This thing right here preserves that identities. Yes, identities are important. Nowadays we have such great identity crises that okay, I'll just shut up and not make such horrible jokes. So here I have this is the diagram. This is the diagram that one is to box and say that this diagram shows this is what it is. And now we show that it preserves identities. What were identities like? Identities were like this, all the, so suppose you have here this set, this family xi indexed by I, and you have this morphism, and you have this morphism identity, which has the data of identities of all these object xi indexed by I. Suppose you apply again the functor to it, fam f, what you get is, first of all, the objects get transported like how they are supposed to be transported. F of xi, right? Index by I, and the images are transported like this. Let's see, this map would be then something like f of id f of id, it will have the data functor, it will have the data functor of id of all these spaces xi sub I, but we know that it is f is a functor, therefore you get id of all these f of xi points. Therefore this is identity morphism, therefore this is also the identity morphism. Yep, so there is this property of identity preservation. And therefore we see that fam f is a functor from fam c to fam d. Right? Yeah. Yeah. There you have it. We showed that given a functor, what is this functor fam f going from fam c to fam d? Okay, I mean, that is a lot. That is a lot of stuff right there. And we only started here. What is fam? We have tons of questions to answer. What to do with this diagram? What to do with this diagram? When we started, the stream was already, we are already 2.5 hours into the stream. Let me just check how far we have made it till now. It is 3 hours and 42 minutes. This stream will go for at least 6 hours. I can see it. The stream will go for at least 6 hours now. There's no saving it. Let me just have a breath, catch my breath and all that. And then we still have another thing to show, that it sends so we have so we showed this as well. We showed that fam sends functors to functors. Now what remains is to show that fam sends natural transformations to natural transformations. Okay. Is that called fam of alpha? Oh my goodness, fam of alpha. Okay, so I will come back and answer the question Given this natural transformation, alpha from the functor f to the functor g, both functors being from c to d, what is this fam alpha natural transformation from fam f to fam g, both being from fam c to fam d. Okay, that is a question that we have to answer after I'm back. I'll stop the audio so you will probably miss the nocturne, but yeah. This is why we started, all this. From the humble homotopy of paths, homotopic maps, homotopy of maps, not homotopy of paths, homotopic maps, deformation, retraction, homotopy of spaces, homeomorphism, homotopy equivalence, then we looked at the homotopy extension property, right? So we tried to prove something, the homotopy extension property, all these crazy diagrams that I was drawing, all these inclusions, all these push outs, and it was the next live. Yeah, then I whooped out some paper using the clanker to finally look at the proof that I was unable to get to myself. Then it was already way too late at night, so I started yapping about some category theory. Yeah, then in the next slide we completely did a different thing. We did some tilings. I'm not really that serious about these tilings. Then these are discussions I was having with a friend of mine. Then recently we started with homotopy of paths. It was probably the day before yesterday's, last morning's, it was the day before yesterday's live. Homotopy of paths, all these crazy drawings I was copying down from Hatcher, and that stuff. Path homotopy defined. There is an equivalence, homotopy of paths. Then we first time defined the fundamental groupoid that we have been yapping about all this time. Shows that this composition is well defined, associativity and all that, identity. Yeah. So we showed that pi1 of x is indeed a groupoid, and then this crazy diagrammatic argument about this. What was this, by the way? That all morphisms. This diagram directly shows that the fundamental groupoid is indeed a groupoid, that all morphisms have inverses by the reverse path. And how do you shrink the reverse path? How do you make the reverse path homotopic to the constant map, which is the identity? So it concluded the pi1 x was a groupoid. There started this huge onslaught about how to get from top to groups. I first took the wrong way, having to select one object, and then got a fundamental group and all that. So yeah, there's this loop. We define the loops in space. Loop space, we define omega. Loop space. Oh, today I defined omega as well, so thankfully these are the same things. Yeah, there is this thing. Omega was a functor, so yeah, that expressed omega as a functor. Of what? Functor from where to where? I don't know. It's just a set, functor to set probably. homotopy, equivalence on, morphisms on top. Yeah, so this was some of the things that homotopy is equivalence on. What is the delta, by the way? I have no idea. Delta top star, I have no idea what is delta top star. Maybe the discrete category. Oh, it is delta top star is the discrete category on top star. So there are no other morphisms, no continuous maps. Only continuous maps are self maps that fix the base point and all that. So there is that. X is path connected, and we saw the relationship between the path connected spaces and stuff. We saw for the first time how pi 1 of x moves to a group, what it does to the fundamental group, what a morphism or a path class in the fundamental group in the fundamental groupoid, how does that give an isomorphism between the two groups in the two fundamental groups. And I was trying. Then this is some weird stuff. Oh, okay. So this is some weird stuff that I was trying later on but could not. There's that. So there we define inner automorphisms of groupoids, simply connected space and pi 1 and all that. So groupoid has objects and only this stuff. Let x be an object of the groupoid, and aught x is index is a group. Similarly, aught y is also a group for y object. If there is a function, if there is an arrow f from x to y, then aught of y is that thing, and aught of x is isomorphic to aught of y. Kf is an isomorphism. This kf we produce inverse blah 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 and all that. Turns out the inverse of kf is kappa of f inverse. So there is that. If space is path connected, then all the objects of the fundamental groupoid are isomorphic. So there is basically only one isomorphism class of the fundamental groupoid. So there is basically just one unique fundamental group up to isomorphism. Each path component of a space is an isomorphism class of the fundamental groupoid. So there is this kind of equivalence between the quotient space, the path connected spaces, and the fundamental groupoid, discrete category, and all that. X is simply connected if X is path connected, and fundamental group is trivial for some base point and all that. Path independent isomorphism between this if and only if both groups are abelian. So that was a very strong thing we showed, that the isomorphism the isomorphism kappa generated by the isomorphism between two fundamental groups at different base points, that particular isomorphism is the same map independent of the path f we choose between these, is basically independent of the path f we choose if and only if both of these fundamental groups are abelian. We showed that. So there is that. So here there was a summary chart of what we moved to. So this is the fundamental groupoid. We saw that if x is path connected, then pi 1 of x is all objects isomorphic, and all the fundamental groups are basically isomorphic. If isomorphisms between these fundamental groups are independent of the paths or path classes or isomorphisms from between the 2 points, then pi 1 of x are abelian. All of these are abelian. If and only if one isomorphism, there is basically just exactly one isomorphism. There is exactly one isomorphism. If there is exactly one isomorphism from x0 to x1, or there is exactly one path class, that means the fundamental group is trivial. This is the most special thing, the simply connected space X. So Then we looked at some topological categories. Pi1 is a functor from top star to group and all that. We looked at what top is, what top star is, what h top is, what h top star is, and all that. Now I was teaching some guy. And then comes today. We started with this diagram that we had in mind previously, and then we showed some of the things, that aught is a functor, that pi1 is a functor, and that the fundamental groupoid was a functor. We showed those things. Pi1 is a functor, here it is, homomorphism. So then we saw that there is that some of these discrepancies cannot be really resolved, that these things do really actually depend on the actual choice, so there is no way to eliminate the choice. And what even this is, well, no one knows. This probably does not exist because this did not really pop up in what the clanker said, so that one was probably a bad idea. So then we revised our plan of what we want to do. So we decided that we instead want to have a solid functor to the family of groups, to the fam GRP category. And to understand what these things are, so let's say what this aught is, what this fam is, what this sec is, we decided to look at what this fam is. So fam is a 2 functor. Then we just saw what kind of a functor is a fam which moves basically takes a category and gives another category, fam of C. Then what kind of a functor is fam which takes a functor and gives another functor between the two fam categories. And now we will see what kind of a functor is this fam which takes a natural transformation between two functors and gives another natural transformation between the two fam functors. So yeah, this is all the stuff we did so far. This was all this getting started on YouTube, studying live, and now we are here. What is the time? It is 3 o'clock. Yeah. Let's do this. So given this natural transformation, what is fam alpha going to do? Okay, let me just guess this one before I look up the answer, what the answer the clanker has given. So just hold up a second. So morphisms look like this. So morphisms carry this data. So yeah, objects look like this. Morphisms carry this data. The identity morphisms look like this. Composition of morphism looks like this. And we saw what functoriality looks like this, where the morphisms get sent, and that happens quite in a very natural way. And let's see what this does to a natural transformation. So a natural transformation, of course, has a collection of data. So there is this map alpha of x. There is this morphism alpha of x for all x in the category C. There is this morphism alpha of x in D from f of x to g of x. So natural transformation, so alpha is really this family of maps alpha sub x where x is an object of C. So where should this oh okay, not just this, a natural transformation has some more properties which I do not in fact have written down in front in my notes or anywhere, so I'll have to consult a book. I think I will consult a Wodi this time. Yeah, so this live started that many hours ago and this is the first time I'm opening a book. Anyway, not that bad. Let's see, where is a natural transformation thing? It was defined somewhere. Constructions for categories before that. Definition of a category, not really here. A functor, example, daily, isomorphism, constructions of categories. Is it not here? Free categories. Where is natural transformation? Foundation small, locally small. Okay, looks like we do not have natural transformation here. The generalized element, products. I did not read so far, but I have read natural transformation, so it must be in Leinster. So yeah, we are looking at Tom Leinster. Yeah, Tom Leinster has functors, faithful, yes, natural transformations. A natural transformation, let A and B be categories, and F from A to B be functors. F and G from A to B be functors. A natural transformation alpha from F to G is a family of maps alpha sub A from F of A to G of A for all A in A of maps in B such that for every map A to A dash in F, the square, okay, that square commutes. So that is the only necessity that we have to satisfy here. So here, basically here in categories, we encounter for the first time a commutative square, as in first time in main theory. So we such that for all f from x to y in C, this square commutes. What is this square? The square is f of x to f of y through ff. You naturally, okay, now you apply alpha to it, you naturally transform this to, naturally you apply alpha x to get here g of x, you apply here alpha y to get here g of y, and this gives you gf. So this square commutes. This is this kind of a commutative square, not exactly this kind, but yeah, all commutative squares are not the same. Such maps alpha sub x are called the components of alpha. Sorry. Okay, so that is what a natural transformation is. Now, given this commutative square, we can of course apply fam to it, right? So of course, whatever that natural transformation fam alpha is, it of course will have some components like this. Fam alpha will have some components. Let's call this oh my goodness, x, like this, where x is this kind of a family of maps, xi, like this. So yeah, let's see. So what you do is you start with what do you even start with? You have these transformation fam f, these functors fam f to fam g in the fam worlds, right? Not really sure how to apply these. So applying these functors, you get, so what really is fam f of this, fam f of this object is really this object, right? So we write that kind of a stuff. So f replaces all these. This is going to be big commutative square. F xi I. Here you have f yj j. Suppose here we have some kind of a fam f map. What are the morphisms in fam C, by the way? So for any morphism in fam C from this this collection of x to this collection of y, just a second, I cannot write this cal y, yeah, maybe like this. So it is like this, right? Okay, we have this f. This is in fam C. You apply fam f on it, the functor f, then you get a map from actually I don't even know what is going on even at this point. Yeah, I have no idea. Oh, so okay, this entire diagram, we know that this entire diagram is in the category D. So this entire diagram is supposed to be in the category fam D. So fam f of f is a morphism in fam D. Okay, that much is clear so far. So there we have this natural transformation alpha, this curly x, and alpha of this curly y. That was really bad. Like that, I guess. That is probably the best I can do right now. Okay, this arrow really looks like the Tixi arrow. Okay. Here you get this g of xi, g of yj, this is fam f, this is fam g of f. So for natural transformations, these should be it, right? So fam alpha so since alpha is really this kind of a family, we see the fam alpha is really this kind of a family, alpha sub, let's say, this calyx, such that this calyx are objects in fam C, subscripts of subscripts, such that this square commutes. So yeah, there we see that is what this fam does to a natural transformation. But I'll just check once again in case I'm missing something. Natural transformations. Here's a natural transformation. Fam alpha is a natural transformation. This by excuse me, what? Fam alpha sub ix excuse me, oh, okay, now I see. Now I see. So yeah, that is basically it. But we have to remember that this I and this J are really coming from those distant lands of this category C, fam or fam C. So this diagram is in fam D. And yeah, that is what a natural transformation is. So as you can see, gradually the requirements of space of how much we need to define and how much machinery we need, that gradually decreased. So now we have successfully answered the first question: what is fam? My goodness, we are not even close to going to the second question. We now have to look at what these things are, what fam top and fam pi 1. We know what fam pi 1 is once we get to know what fam top and fam gap are. But my goodness, then we have to know what this ot is. Man, this is so much fun. Never had so much fun in my life. This has been going on for 4 hours and 17 minutes now, and I have no idea how long even more, how longer we actually will be pulling this through. Okay. Okay, fam top star is of course the category of families of topological spaces. Um, Objects are these. Let's see. I'll make a hierarchy right now. X, just this straight X, this would be a set. This is just a set. This with one side curl and one straight, that is a topological space. And this guy with both sides curled, goodness knows what it is. It is probably an object of fam top star. So this is a set. This is a set. This is topological space. Okay, so this is an object of set, this is an object of top, this is an object of fam top. Okay, so this is the convention. Objects are of this form. Objects are of this form. These are objects, and well, morphisms are like this. Actually realized that I should be calling them like this. F is a set function which maps the index set I to the index set j, and there is this family phi I for all I. So it should look like this, or rather there is a cumbersome way of writing it like this: F and phi I, this entire family indexed by I. But this is way too cumbersome, so I'll just write it like this. The morphism on top we have F, below we have the family data. Family data sounds weird, yeah. And this is, let's see. Okay, I understand now. The conventions. Similarly, let's do this for y as well. This is yj, this is j, where we send wait a second. Oh yeah, what? Wait a second. This is the object, right? This is the object. Oh, okay, this is sent to this. Hold up. I don't understand. This is this. What? Oh yeah, now I get it. I got confused by what even this was. Where phi I is a map from xi to y f of I in top star, in fact. Oh yeah, this is fan top star, right? So okay, just oh my goodness. So the thing is that I'm supposed to be writing these like this, because that is what the objects of these are. But I can't. I just can't. I'll have to. You cannot just make a convention and then break it. You're not politician, you're not global politician. You cannot just make a convention and break it. My goodness. This is the map data. These are morphisms. So yeah, that is what FamTop is. So now, then, what is this sec from top to FamTop star? What is this sec? So we are going to look at what this functor is, and yeah, for any topological space X, sec of X is this. Sec of X is this object. It is this topological space followed by X, or yeah, followed by just X, okay, where this X is in X, where X is the underlying set. Okay, so this is the object. So of course, for any morphism, for any map from X to Y, let's see, there is sec f from sec of X to sec of Y, given by the morphism looks like this. Sec of f carries this data. Sec of f is this. Okay, alarm. Just wait a second. Sec of f carries this f, and I'll be back. Okay, yeah, so sec of f carries this data f. So f is the index. The indexing set is this X. So index is underlying set X. Okay. F, and this map. What is this map? What should this map be? This is a bit unnatural. You have to have a family of maps, right? Let me see. So it should look like this. It should look like this. It is this family. So the morphism is this, and phi x is supposed to be a morphism from this pointed space, this guy, to this guy, such that this, of course, okay, such that phi x, okay, now I get it. Okay, so these are individual map. Phi x of t equals f of t. Pardon my hilarious, absolutely sacrilegious notations. For all t in x. For all t in x. Okay, so that is what a morphism is. I'll come back and prove that sec is a functor. So it preserves identities and compositions. I'll be back in 2 minutes. So I'm back with some stuff to eat, but I have no idea how to eat while simultaneously also writing, but I'll try. Okay. So I'll probably start eating first before writing, because of course there is no one watching me. So this basically turned into ASMR food blog / math. Okay, so this is what it acts on morphisms. Now we have to define how it basically preserves compositions. Okay, let's see that. Sec of, let's say, GF, or rather let's see. Okay, I'm not really sure exactly what is going on. How did we show the morphism compositions here? Oh, exactly, from the data. Sec GF is equal to this. Wait a second. sec gf would be equal to gf, and let's see, what should this be? We do not have any raw data at hand, but phi, psi, let's call this the weird phi of x. Let's see, this family, where weird phi of x is from this to, let's see, this to g of f, or okay, just to hell with it, g of x. I guess this is that, and weird phi x of t is equal to gf of t for all t in x. Now we are going to slightly break this down as being our target is to show, after all, that sec gf is equal to sec g and sec f. So we are going to show that. How do you bring it towards sec f? Compose sec g. Well, that will be weird. Now look at this. Let's look at this composition. Sec g, sec f. Sec g has the data g and this family psi y, such that y in y. Sec g has this data, sec f has this data f, phi x, such that x in x has this data. So this composition will have the following data. It will of course have gf here, that is not a question, but the composition, as we saw there, just wait a second. What are the compositions here? Composition will have the form this. So that would be, it would have the form this: psi f of x, phi x, such that x in x. It will have this data, right? This is the data that it would have. Now what does this guy do? Here, where psi f of x, phi x is all, of course, from this. Let me just do this diagrammatically. X, this has the morphism y f of x, which is given by phi x, and this has the morphism phi sub f of x, psi sub f of x, which goes to this g f of x. So in the end, we see that this psi f of x, phi x, goes from x comma x to z comma g of x. That is true. And we see that for all t in x, psi f of x, phi x of t would be, first of all, phi x of t is equal to g f of t. So psi f of x, that would be f of t, and that is equal to g of f of t. So that is in the end gf of t. This does match with phi x. Therefore we see that for all x in x, this weird phi x is equal to psi f of x, phi x. Therefore, basically we established that sec g sec f is equal to sec gf, right? Because there is no leeway. If we have a family of maps like that, indexed by x, and we have another family of maps, and those maps are defined to be identical, because this condition that this holds true for all t, that is very, very strong. So that restricts that there cannot be two distinct families like that. So if two families satisfy this thing, then it must be that they are equal. They both are the same families. So that is what we get. Now let me eat. Let's see what we got next. We just need to show another thing to show that sec is a functor, is that it preserves identities. To show that sec preserve identities, we just chuck this into the data. So that is, consider the identity map. Consider idx or idx from x to x. Now sec of idx would be, of course, this, as we defined here. That would be identity on this set x, and what? This family of maps which sent this family of maps, right? Or rather I should say, yeah, that it's okay. This family of maps identity, this family of maps which I will call now J, from where to where, x comma x to again x comma x. Let's call this Jx, such that x is in x, this data, where now we see the magic that Jx of t is equal to id sub idx of t for all t. Therefore Jx equals identity for all x in the index set x. Now that is exactly what the identity morphism was. Recall here, composition identity morphism is this. Identity morphism is this identity of the index set and identity on all the individual sets. So we see that Jx is identity on these sets for all x. Therefore sec of this identity on x is equal to the identity of the sec of x. Therefore we see that sec is indeed a functor. From where to where? Sec is a functor from top to fam top. Not just fam top star. There you go. We found a way to get this. Okay, it's getting cold, so I have to finish this. So after that we will be looking at what will we be looking at? We have looked at sec and how sec gets us from top to family of top star. Now notice that we know this is no fantasy land. We know that top star to GRP we have the fundamental group functor pi1 is the fundamental group functor, and we also saw that fam is a functor. Wow. So fam of pi1 is a functor from fam of top star to fam of GRP, and we are going to leverage that. This is going to be fun. So we'll be basically looking at what exactly fam of pi1 does. Yep, I'm back. So we are now going to look at what top star of pi1, what basically fam of pi1 is. So as promised, fam of pi1 is a functor from fam of top star to fam of group. So fam of top star consists of objects like this, I've already done that above somewhere. Yeah, the objects are like this in fam of top star, fam top star, family top star, blah blah blah. The objects are like this. The morphisms are like that. The morphisms are like this. So what this does is, check this out. Yeah, by the way, a functor gets assigned to a functor. Okay, yeah, like that. We have to tread a bit carefully here, and that is because yeah, we have to just tread a bit carefully. Given a functor, what does fam of functor do? Given I think I'll just take a copy of this thing right here with me down to where we are basically working and looking at things. I'll take a copy of this. Yeah, there is a lot of data. It is still not giving me any option to do anything. Brother, I want to make a copy of this. Will you please allow me to? Oh, it is up there. Should be this. Bruh. Okay, anyway, I'll try again. Let me make a copy of this. It misses out every time like that. Sorry, what was the second option? Oh, it was copy. Sure. I'll paste this. I will paste this. Holy moly. It did not get pasted or something? It did not get pasted. I have no idea how this works. Wow. That was fabulous. Yep, let's make this so small that I can carry it. Basically, it is carrying this down from one empty spot to another until we reach where we want to. I have to be sure to not miss data, like not miss some things that I have to copy. So far it has been going well. Yeah, finally got a copy of this down here. Now let's just re-expand it. Kind of like that. Maybe this. Yeah, that is a rather high quality. What happened to the internet? Yeah. Anyway, so I do not need this that big. I just need a few small things to look up from here when I need it. Given a functor, what is this? Okay, so okay, what does this do? First of all, we know that given some family of pointed spaces xi, xi indexed by I, the functor, which is fam of pi1, would send all of these to this family. First of all the fundamental groups pi1 of xi and xi indexed by I. First of all, this is what is going to happen to an object. Then let's see what happens to morphisms. Suppose we have continuous functions. Suppose we have morphisms here, xi, xi, I, to suppose we have a morphism like this. These are j indexed by j. Morphism is like this, f and phi I indexed by I, which go like this, that phi I of xi is equal to f of not really, f is that kind of a data, right? Okay, phi of y f of I, there's that, and phi I of x is in and basically phi I is a map from here, or rather let's call it here, to y of f of I. That is what it is. Okay, suppose we have a morphism like this, then we take all the induced homomorphisms, or pi1 on all of these. So then we have a morphism from all these fundamental group families like this, xi, xi indexed by I to indexed by j, not I, given by, let's see, pi1 of f, and all of these maps are like pi1 of phi I indexed by I, such that pi1 phi I of xi, hey, wait a second, So every continuous map gives a homomorphism, right? How does the induced homomorphism actually work? Let me just recall. It was somewhere up here. Yeah, it is this. Pi 1 is from here to here. It induced homomorphisms. Okay. Oh yeah, I'm an idiot. Why am I putting xi as the arguments here? Pi 1 of phi I is supposed to be a homomorphism from pi 1 of xi to pi 1 of y f of I y f of I. It is not very visible, but I believe you can see it. So yeah, I guess it will do. I gotta check another thing though. Hold on a second. But I know that the image quality is really poor. But with this tablet I have, this is the best I can do. So yeah, if the channel grows, I'll maybe upgrade the kit someday. And this is not really like serious channel content, I'm just studying. So yeah. Okay. This is supposed to be a homomorphism such that what? It is supposed to be a homomorphism such that pi 1f of p is this. At this point I have no idea what is going on. That is first things first. So yeah, pi 1 phi I of, let's have some map morphism pi here. That will be equal to pi 1 of, that's not pi 1 but rather just phi I compose pi. I put the I even in the wrong place. This will be something like that. Okay. So what this essentially does is we have basically a disjoint collection, a disjoint family, where there is a pointer space, there is a pointer space, there is a pointer space. There are a bunch of pointer spaces, and from these we get a bunch of morphisms. So basically a family is like you put some spaces in there and you bundle up all these morphisms into one morphism like that, and this goes into another space like that, this goes into another category, another family. You bundle up the morphisms like this, suppose it is like that, this, and it goes out like that. Yeah, so this is the stuff. This picture looks great. I guess we do not really need to have this anymore. Yeah, I can just delete this. So this is so far done. How far are we actually? We have looked at this, we have looked at this, we know what this is. Now the only remaining thing is to look at the OT functor. So yeah, let's see. Also, after that, in the end, we will have to show that this diagram even commutes. So there is that. And not just that, that would be just one aspect of one thing I wanted to do in today's stream. So is it then didn't end up being more fundamental groups and circles and all that. It just ended up being more fundamental. Just more fundamental. More and more fundamental. This has been going on for almost 6 hours now. So yeah. I said the stream will be long, but I don't think it will go this long. It is 5 a.m. almost here, and I don't really actually feel sleepy right now. Yeah, so maybe 8-hour stream, 12-hour stream, who knows. 12-hour will be extreme because after around, let's see, how long? 3 hours, and I can go on for at most 3.5 hours from now, unless you allow me another like meal break for breakfast, so I can like just keep streaming. But I don't think that is a very good idea. Also, I'll have to then edit this video at so many places. But okay, it's okay. We can go on for some time. So now we have to see what is the lore of this OT functor. What is this OT functor all about? And just a second. Okay, so um, let's proceed. Ought is a functor from groupoids to family of groups. What does this do? It takes a groupoid G, and out of G is this family. For now I'll denote G and object class of G to be the same thing. So there's that. It takes a small groupoid, so it is not an object class, it is an object set. So out of G is the following set of groups. It is automorphisms of each ought sub G of all of these objects, all of these individual objects. For each object, let's see, what do you even call them? Let's call them G. So that G is in G. So yeah, basically this is this. It is a functor. So in a groupoid, okay, so we have to consider groupoid functors as well. So there is a groupoid functor which gets mapped into an ought functor, and all sorts of messy things like that. Did I look at groupoid functors at some point? Not really sure about that. Ought functor. Ought P is an isomorphism. Okay, this is a different ought. This is just a simple groupoid ought. Did I look at groupoid functors? I don't think I did. Path independence K, groupoid as objects. Is this it? No. Did I not look at groupoid functors? Loop space. Is a groupoid. If I did not look at groupoid functors before, then well, fine. So groupoid functors are just functors between groupoids. There's nothing new with that. It's all old stuff. New names. Let me just have a brief look at groupoid functors here. Let's use this guy. There's a groupoid G, there's a groupoid H. Let's denote them like there's a groupoid G, there's a groupoid H. Suppose there is this functor F between these groupoids, and let's see what do they do for some isomorphism from, let's see, G to H. We get an isomorphism here from f of G to f of H. So that is just a groupoid functor. Such that let's see, f of f1, f2 is f1, f, f2, So also there's that. And yeah. This is supposed to send one groupoid functor to another groupoid functor. I think the most natural thing to do here would be like this. My claim is that isomorphic objects in groupoids must be mapped to isomorphic objects by groupoid functors. G, suppose this G and H are groupoids, there is a functor F between groupoids. Let's see, G and H are isomorphic in G, then F of G is isomorphic to F of H in H. Why is this the case? Because if they're isomorphic, there exists a morphism between them. This means there exists a morphism here. And since this is a groupoid functor, yeah, so all morphisms are isomorphisms. So there we go. But how exactly would this ought go about its way? So it takes a groupoid functor. Suppose it takes this groupoid functor. Let's see, you have this groupoid G, have this groupoid H. Our ought take this groupoid functor. In ought G, ought H, get a functor ought F. What does this ought F do? So we have here these things. So ought G is this, right? This is a morphism. This is a homomorphism. This is a group homomorphism. Nothing to worry about. Or this is the family of group morphism. Whatever. This morphism, therefore, has to be of this form. Has to be of the following form. This ought of F. This ought of F has to carry the following data. First of all, we see that the objects are indexed by the groupoid elements themselves. So the information it carries is first of all this functor, right? Because this is really the map from the index to the index. It carries this, and it carries this family of things which look like this. Okay, this would be wait a second, not really that. What happened just now? Something weird happened. Okay, so this family is not supposed to carry automorphisms. It is supposed to carry what? Out of F, right? So anyway, let's give it just a generic name. phi of g for g and g. This is the information where we know that phi g what do we know about functors? These things. Yeah, what do we know about this? So this odd f really carries this functor first of all, this f first of all, and also carries this thing, this family of f of phi I, this functor phi I, which is a homomorphism. Or is it? I don't know. This is phi g is a homomorphism from the group ot g of g to ot h of what? Ot h of f of g, right? So it is a homomorphism like that. Can we be a bit more precise about what this homomorphism does? Can we be a bit more precise about that? I can feel my brain is starting to stop working. Yeah, I can feel it. This f of phi I is supposed to be a functor, is supposed to be a morphism from f of ai to f of b f of I. What? Excuse me. Okay, yeah, that's okay, that follows. But how so? How do you define it like that? Okay, we have to define it. Defined by the following. Okay. Suppose you are looking at a groupoid object. So yeah, this is what we define this odd functor to be. Now to show that this odd functor is of course indeed a functor, we have to show that. So what do we need to show? We need to show that it behaves well with composition. Once again, how many times did I show something is a functor in this entire stream? There has been at least like 7-8 of them. So we have to do the composition. How to do the composition though? Okay, suppose we have something like this. G to H. When in doubt, always use X, Y, Z. You need 3 letters only. So yeah. Also I need F and G, both of them. So suppose it is like this. This is what we have to show, and okay, so let's get to it. Odd G, odd F carries this data. Okay, now first of all, let's see. Odd F carries this data. Odd F carries first of all F, then carries what? It actually just carries F G times. So basically, yeah, it carries just the same thing. F. It carries F G times. You could just call it F sub G at this point. Odd F carries this, or let me just be a bit more discreet about it. Let's just call them phi sub G. Odd G carries this data. Oh, I cannot use G though. Phi sub X, I have to use phi sub X. It uses G. And psi sub Y, overall Y, this data. So odd G, odd F ought to carry where was that thing defined? First of all, this. It has to carry this data. It is GF here, and the collection has this psi f of x composed with phi x, where we index over x. It carries this data. And now note that odd GF will carry this data. Of course, it will carry GF. Then it will carry some weird phi x index by x where, notice here, we saw that this phi x of f would be equal to gf of f, gff, for all f in the automorphism group of what? Automorphism group in Z of x, or no, of gfx, this guy. And here we know that psi fx phi x of f is first of all equal to psi fx of, let's see, this. It is this. It is f, and that is equal to it is of this form, right? G goes there, it comes here. Psi, because of a psi there would be a G, ff, oh, there just would be a GFF. And this would be inside aught Z of, let's see, G of fx for all f and s. I'm sorry, I made a mistake there. This is supposed to be inside here, and for all f inside aught x of x, for all f in aught x of x. Therefore we indeed see that phi x is indeed equal to psi fx phi x for all x in x. Alright, therefore this family is equal to this family, right? So indexed over x. Therefore this aught g aught f is equal to aught gf, and that shows it that this aught is indeed a functor. So now what do we have here? In the end, after all of this, we have defined all four functors. Now this is not the end. There is still one thing remaining. We have to show that this diagram commutes, that this is a commuting square, and that is another hassle. So here we go. We have to show that this square commutes, right? Let's reproduce that square in the end there. I can't believe I got just time to do one thing, just one thing, after spending like so many hours. Let's reproduce this. Is there a way to copy this? This should be the way to copy this. The second one does not do anything. Yeah, nice. Yeah. We have to show that this diagram commutes. So, le français. What did I say just now? Okay, so we have to show that this diagram commutes. What does it take to show that this diagram commutes? We have to show that OT composed with pi1 is the same functor as fam pi1 composed with sec. That is what it takes to show that this commutes. I would like to change the color actually. Not to this, to this. Yeah, let's move this. That is what we have to show, right? So pick any topological space. For any topological space X in top, see that we have to show that these two objects, OT of pi1 of X and this fam pi1 of sec of X, these two are equal. We have to show that. How do you show that two objects are equal in fam GRP? We have to show that the index sets are equal and all of the indexed sets are equal. So what is the index set? We have to show first of all, index set of OT pi1 of X. Now we know that index set of any of this was the same set as this. Index set of OT pi1 of X is just pi1 of X, or the object class of pi1 of X. Now the object class of pi1 of X, or rather I should write this actually. This is the object class of pi1x, and in fact that is just equal to the points in X. So index set is X. Index set in what? Fam pi1 of sec of X. What is the index set of sec of X? In fact, the index set of sec of X is X. What is the index set of fam pi1 though? The index set of fam pi1. Well, index set of fam pi 1. um, so when is this even passed into there? Turns out I never looked at fam pi 1. Fam pi 1, what is fam pi 1? It is a functor from fam top star to fam grp. So okay, so turns out the index set is the same as that in fam top star. So okay, that is the same as the index set in that thing sec of x in fam top star. Now the index set of sec of x is, we know that to be x itself. So we saw that here, that index set of sec of x, sec objects are, oh my goodness, sec of x is just x. So the index set actually matches out. So what we get here from each for each topological space x, for each x, we get a family which is first of all indexed by x, family like this, which is indexed by x, or in fact even better, indexed by some x in x. And what are the objects of this family? So the actual let's look at the actual indexed objects now. What are the indexed objects in this family? The indexed object of out of pi 1 of x, for out of pi 1 of x, that is equal to the automorphism groups of each x in x. Is that so? And of course the pi 1. And in pi 1, what is the automorphism group? In pi 1, the automorphism group is the endomorphism group. So that is basically Hom of x comma x in pi 1. Now we know that in the fundamental groupoid, the Hom set is exactly this. The Hom set is P of x comma x. Of course, not just that, but we quotient that by path homotopy. We know that this is the object, this is the Hom set, and this is the endomorphism, or this is just the object, and this is the Hom set in the fundamental groupoid. So writing down explicitly, it is the family of all these maps, all of these maps from I to x, such that f of 0 equal to f of 1 equal to x, and this family is indexed by all x in x. So this is the broadened out, written out answer we get. And now from the perspective of fam pi 1 of sec of x, what is the object class of sec of x? For sec, the object class is this. The object class is this. So for a topology, for the space x, the object class of sec of x looks like this. Family of fam pi 1 of this guy. It is this set for x comma x such that x is in x. It is this. Now, what does fam pi 1 do? Fam pi 1 takes this and does that. Takes this and gives that. So fam pi 1 gives you the the fundamental groups of all of these pointed spaces indexed by the set x, and that you expand the definition of the fundamental group. The fundamental group, not really, this is slightly mistaken. This is slightly mistaken. I forgot to do the quotient. And the quotienting is probably the most important part. We quotient this by the path homotopy equivalence. This thing under the concatenation, and we know this thing is also known, this thing right here, this thing right here is also known as the fundamental group of x at x. So that is indeed equal to the family of all fundamental groups based on the space x. So we have finally found the long sought answer of what exactly this functor was. So we have really constructed this commutative square which takes a topological space and gives the family of all the fundamental groups that we need. Now what we can do here is put this choice function evaluation at x here. So that gives from this family of all evaluated x naught of all of these indexed by x, it takes this family, gives you this one fundamental group which is based at just x naught. So yes, that is really the end of this huge, almost pilgrimage. Define this fam, define all of this just to make this one commutative square, just to make this one square commute. And now it is in its full glory right there. So this was the fundamental group. We wanted to make this commute. So we have finally succeeded in this long process of what we wanted to see, and we finally got to see what we wanted to see. So yeah, from top we select. We do not do any selections here. All the selections are done later on in the process. Yeah, so there is this. But now there are still some things remaining which we need to address, namely things like what music is playing in the background and all of that. So yeah, 6.5 hours. That's a long stream. Gotta agree. Okay. So what to do now? Okay, so this is not the end though. There are some things which is like all these fams. Just the bonus thing after all this, I just wanted to mention that I just wanted to mention this thing, that this category top star, it is just the it is just the I mean it is just the coastline category of topology. Top star here or on top? Yeah, top. It is just the coastline category of in a single space. I mean, yeah. So from the initial object. Free coproduct completions of categories. Just wait a bit. So, I mean, there's not much to do here right now anymore. I think I'll just end the stream here. And for a few curious people, um, okay, never mind. So yeah, this is the end of the run, and it ends with this. So yeah, that is the end of the stream. I'm ending it.